Well, good morning, everybody. So I'd like to just start by, first of all, just thanking the organizers of IoT Next 2015 for inviting me here today. This is actually my first trip to India, and I'm very happy to be here and talk to you all today. So I'm going to start. Let me just say a little bit about analog devices. So analog devices, we're celebrating our 50th year here today, or this year as a company. And we're a world leader in signal processing and data conversion products. And we've actually had a presence here in India for, I think, close to 30 years now at this point here in Bangalore. And a lot of our IoT development work is actually done out of this development center here locally. So the topic of my talk today is IoT, smart partitioning, and value creation in a connected world. So I think that this is pretty salient for the audience here with the electronics and the Indian Semiconductor and Electronics Industry Association, because we hear a lot about IoT and the cloud, right? And so it raises some very existential questions about we as hardware suppliers. I mean, how are we going to create value and add value in this new sort of world or on this new frontier? So my talk today, I'm going to talk about a few different areas. So first of all, I want to talk about the IoT multiplier effect and just how value, sort of the perception of value or what the expectation around value creation for IoT will be. I'll also talk about value creation and value loops. I hope everybody can hear me okay. And I also will next talk about sort of smart and what that really means in the context of IoT. I'll then talk about smart partitioning techniques and some of the areas that we're sort of exploring this, kind of as a sort of some insight as to how to think about solving some of these problems. And I'll have a couple of examples about smart nodes, and also to the audience here, I was asked to talk a little bit about some of the Fab project we have going on in one of our sites in Limerick in Ireland. And finally, I'll summarize. So let me start initially with the IoT multiplier effect. So one of the things, and there's been many reports about this, I think we heard some slightly different numbers on this earlier this morning. So, one of the expectations is that in the next sort of few years, actually I just have a question for the folks that are on the monitors here. Is there a way that I can see? Wait a minute. Now I can, excuse me, now I can see my slides. Move out here. Okay. So over the next few years, it's kind of expected that the whole economic impact of IoT will be somewhere in the region of about $2.7 trillion. And there's different estimates around this from different sources. But the key drivers behind this will be improvement in efficiencies in healthcare and manufacturing. And but of course, a lot of technology is going into enabling this. Okay, so looking at sort of the area of services and semiconductors and also systems in general, right? We're going to see a substantial growth in the business and of these areas in the next few years, right? And I think one of the things that is very clear is that although semiconductor growth is going to be pretty substantial, we're also going to see fairly explosive growth in the area of services. Okay, and so. So this, to summarize, I mean, we're going to see a substantial growth through the instrumentation and applications in healthcare and manufacturing, and then also substantial growth opportunities for the supply chain like ourselves that will enable all of this to happen, okay? And, the interesting ratio here with these numbers is that, although the growth in the industries and the supplier industries will be somewhere in the realm of about maybe $260 million, or billion dollars, excuse me, the economic impact is almost 10 times that. And this is sort of sometimes referred to as the IoT multiplier effect, okay? So let's spend a little bit of time talking about value creation, okay, and in IoT. So the question we really have to think about is how will this multiplier effect be enabled, okay? So the first thing is that, the real impact here is going to be about changing behavior, right? So we're almost moving from reactive, systems to predictive systems or preemptive systems, right? So the idea of you're preventing something from happening rather than waiting for something to happen and then having to fix things later, okay? So a good example is in predictive maintenance on machines, right? You don't want a machine to fail before you figure out what you have to fix. You'd like to know ahead of time and therefore can prevent it from breaking and minimize downtime effects and all of the negative aspects of having to unexpectedly take a machine offline and fix it, okay? And, the overall solution value from this is going to come from this ability to modify behavior, but it kind of requires a loop to do this. So this graphic, which I hope you folks can see, I'll just talk through it, is from a recent report from Deloitte talking about the value of information, the information value loop, right? So it starts, I'm going to try and use a laser pointer here, sort of, we're in a system where you've got some action in the real world. Well, we use sensors to detect that action and the result, consequence of that action. We've got some electronic systems that will essentially measure that, okay, and actually convert that into real data, okay. That data gets communicated over some kind of network, and then, there's a variety of technology standards that are involved in kind of making this happen, okay. Data gets aggregated, so we look at data from many different sources, many different sensors, okay. At this point now, we start to sort of, make some decisions or, try to understand what's happening in the system itself. And we apply some analysis or analytics, and then really try to estimate sort of what behavior changes need to happen before we infer some action in the real world again. So what I love about this chart is that it talks about some of the major kind of, the various stages of this loop, some of the technologies involved, although at a very high level, but also some of the value drivers. Now, it's really kind of hard to see some of the text in here. I didn't realize this was going to be so small on this screen. But there's different areas that are like around security, risk management, timeliness of data. Where if we can reduce the risks associated with, for example, security, improve the timeliness and latency of data, so you can do much more real-time analysis, then we can start to add value to these systems. So the key thing about this is that, as I want to talk about in a few moments, is that before behavior can be modified through action, we really have to do a good job at analyzing what's happening in the system, and so we can decide what the most appropriate action to take can be. And that really encompasses looking at this part of this value loop here, this information value loop, almost everything up to or excluding the action, and that's what I'm going to talk about next. Okay, so through this journey around the loop, sensor data is progressively transformed from sort of raw data to more meaningful and actionable information, okay? And there's a nice model for this. Some of you may be familiar with Ackoff's DIKW pyramid. This idea of looking at data, information, knowledge, and wisdom, where essentially you start with an awful lot of data, and progressively as you move up the, add more sort of intelligence in here, you can extract more meaningful information, provide context to gain knowledge, and then really apply it in the form of wisdom, okay? So the example I have here, it's kind of funny enough, there's been some comments from earlier today about the traffic here in India. And I swear to God, I did not change this slide after experiencing traffic for the first time yesterday. But this is a good example of just a red light, okay? So, so at the data level, you detect a color red, okay? You add some, information or extract some meaning for that, knowing that this light is located on a certain intersection and it's just turned red. You provide some context by the fact that you're in your car and you're driving towards that introduction or towards that intersection quite fast. And so, and then when you apply wisdom to this, you decide, okay, well, I probably should stop the car. And then the next thing is obviously to, step on the brakes, right? So progressively as we move through this, we're adding more value, right, or extracting more value from this information. And that is sort of all of these different levels are areas that we can start to think about how we create value for our customers, right? Where are we playing in this type on this information journey? Okay, so now I want to talk about what does smart mean in the context of value creation in IoT. Okay, so let me just take the DIKW for a moment and just move it on a horizontal chart here for a moment. And so if we look at the various stages along the way here, all right, these various kind of, transformations, okay, so typically in an IoT system, you're going to have some kind of sensing, data conversion on the network edge, okay. There may be some processing you do locally to the network edge. There'll be some gateway device. I mean, it could be, it's you're part of a sensor, a fusion sensor, like a wired sensor network, or you could be over wireless. But basically, there's some kind of edge node or gateway device that communicates that information up to the cloud or to some kind of server-based services. And then in the cloud itself, There's some kind of pattern recognition that happens, like using big data analytics. This could be usually looking at data over very long time records, potentially lots of different sensors, right? Lots of different data inputs. And then the final area is that, where you start to apply some predictive analytics or machine learning techniques to kind of enable decisions to be made, right? And this is where you're sort of estimating what the best course of action or best course of behavior can be. Now, one of the things, of course, we see with IoT is what's happening, right? And we've heard examples of this earlier today, is that IoT is starting to enable the increasing automation of this process. I mean, we as humans have done this for years, for millennia, right? I mean, we think about our environment, we react to it, right? And we try to make the best of what's around us. But really, IoT and the technologies around IoT are increasingly enabling the automation of this process, right? And therefore enabling an awful lot more efficiencies. And so, as we look at the various steps along here, right, all the way from, the transformations of, basic raw sensor data or, physical phenomena in the real world to data, all the way up to, deciding, to take an action or what that action should be. Each one of these steps is like a smart step, okay? So, and each one of these steps provides an opportunity for us to add value in an overall system, okay? And and then, whoops, sorry, the clicker stopped working here. Oh, okay. So I think these steps are key, right? And this is kind of, as we think about, our businesses today, the type of things we do, right? And as we look to sort of add more value in these systems, examining kind of how we can, look at these different sort of smart techniques or capabilities to add more value to our systems and help solve our customer problems is kind of a key place to go for gaining some insights. So I want to talk about some smart partitioning in IoT systems. So this is a graphic taken from a Cisco white paper, which is actually a very useful paper, in the context of I believe it was actually part of an IoT World Forum exercise. And it really talks about the various levels in sort of this sort of whole IoT stack, starting with the physical devices on the bottom, all the way up to sort of, collaboration and processes involving people on the top, okay? So, there's various steps along the way, connectivity, edge computing. The term fog computing, I believe, was coined by Cisco as kind of to represent this notion of a distributed compute model, and not just sort of sending all the data to the cloud. And then the various data aggregation and accumulation efforts that happen in between. And, one of the ways we like to think about the world as analog devices, of course, everything is a signal chain, right? And, so when we look at the various elements on the network edge here, right, we have our sensors, the analog signal processing, some digital or data conversion and digital signal processing, and also software, of course, that runs here as well. And really, the gateway and analytics engines are really kind of additional parts of a signal chain where potentially any of us can add value, okay, or run algorithms, or in the context of the overall solution or system you're trying to build. So I'm going to spend a little bit of time talking about some of the pros and cons of different smart partitioning, and then I'm going to give a couple of examples. Okay. So if we look at sort of the edge node, I'll start with that. We'll talk a little bit about the gateway and also on the cloud and analytics side. So some of the pros and cons of processing at different parts of this signal chain. So on the edge node, the key thing here is that you can build these devices with a really, really small footprint, right? I mean, a lot of suppliers out there today have very, very low power and very small semiconductor industry. In the last 15, 20, or even 50 years, its evolution has all been around increased processing power, smaller footprint, and lower power, right? So this enables a lot of intelligence on network edge nodes. You also have the opportunity to do closed-loop feedback because you're very close to the actual phenomena you're measuring, okay? So, it's very hard to do when you've got seconds of latency potentially back and forth to a cloud service, but right on the network edge, you can actually potentially implement closed-loop feedback loops, at least in a more straightforward fashion. They're not impossible into the cloud, but it becomes a lot easier if you're right on the network edge. The other area, of course, is a big focus is around energy independence, the idea that you can build these sensors that are very, very low power. You can use potentially energy harvesting techniques and have them basically be maintenance-free in the field for years, right? So you never have to go back and change a battery or anything like that. Some of the disadvantages is that, there is a small form factor price, right? Power may say, and also you may be limited in the amount of processing you can do locally. It's difficult, it's not impossible to do data aggregation, to sort of compare or use information from other nodes that might be in the network. Okay, the physical security is a big piece, right? These devices, could be existing on lampposts. Unlike, examples of, say, Factory 4. Or Industry 4.0 we heard earlier, where you have fairly good physical security of the devices that are in your plant. Devices that exist like in smart city applications out on lampposts and things like that, there is no physical security, right? So that is an area you have to be concerned about. Remote management and, secure upgrades. Obviously, over time, you need to upgrade the software, potentially as for improvements, but also for security patches and things like that. So doing this remotely, it can be a challenge. And, the data rates can limit the power, or can be limited by the amount of power, right, you want to spend. So we've certainly seen examples where, the single largest sink of power in some of these systems is actually when you turn on the radio transmitter, whether it's to send, communications over narrowband ISM, like 6LoWPAN or some of the low power networks like that. You still spend an awful lot of power transmitting data. So obviously you want to try and minimize the amount of times you do that. So now if we turn our attention to the gateway, this is potentially areas, there's a lot of activity in this space, but where you can do an awful lot more processing, relatively close to the edge of your network on a gateway. Okay, so there's potential for data aggregation with other sensors, and we heard one or two examples earlier, where this gateway itself can actually pull data from a larger cloud system and use that data as part of the signal processing. Okay. There's the, you can do potential network edge analytics, right? I mean, the idea of kind of running, certainly, analytics engines on this, on the gateways is definitely a possibility. And, you have full OS stack capability. Typically, these systems are running some form of Linux, maybe Windows, right? And you can awfully, that really helps when it comes to developing and development on these areas. They're IT friendly and generally more secure, right? Again, there may be some, as I see in a moment, physically, there may still be physical security issues depending on where these gateways are located, okay? So these devices are typically not low power. They may have limited storage and, the ability to pull data from, a large variety of other sources, and also the physical security. And then finally on the cloud side, and I should probably qualify this by saying that, cloud, when it comes to sort of, as a tool for running big data analytics, and machine learning algorithms, doesn't have to be resident on AWS. There's a lot of applications where big customers want to run the cloud services internally on premises just for security reasons and privacy reasons. They don't want the data leaving their plants, right? So it doesn't have to be remotely on it, like I said, hosted by Google, AWS, or Microsoft, or others. But the cloud aspects of this, and this is where the real kind of we hear a lot about the benefit of IoT, is in the ability to sort of deal with very, very large databases, sources of data, and also apply large amounts of compute processing power to data to run machine learning and algorithms. And I think has probably the best security, right? Although everything has holes, right? But in terms of the security is potentially a lot stronger on the cloud side. There's a range of options available, lots of different platforms, whether you want to sort of start with an infrastructure as a service or even use a complete software as a service solution. Okay, and a large variety of open source options and development tools available. And it's very scalable, right? So if you need to turn on more servers and so on to deal with larger data capacities, it's relatively straightforward to do that. So on the negative side, potentially here, I mean, there is server hosting required. Okay, if you're running over the internet, the communications can be problematic, right? And you have to be able to account for that in your systems, okay? And the services can be expensive depending on where you source them, okay? So it's not, data storage over the long term, I think can get expensive relatively quickly. So where we kind of see things going, right, is that today, there's a lot of focus on that the data, kind of gets captured through, sense and then connected to the cloud and really sort of analyzed and at the cloud level. And I think that, that this is sort of going to be really hard to sustain over time, right? Because the transmission and movements of large amounts of data can be very power expensive and bandwidth intensive. So kind of, looking forward, this idea of using smart sensing and smart nodes, where you're starting to do an awful lot more of the processing and interpretation closer to the network edge before sort of sending the results, right, up to the cloud is kind of, we kind of see more as the model moving forward. Okay. So with that, I've got a couple of examples I wanted to kind of work through real quick, and I'm just going to do a quick time check. Okay, I have a few minutes. So the first one is an example of, we actually have this demo at our booth outside, and I know this piece is going to be a little bit ADI heavy, but these are the examples I'm most familiar with. And it's a good example of a video-based occupancy sensing. Okay, so what we're doing is we're taking one of our very low power signal processors, we're running an image processing algorithm on this to extract occupancy information, right? So in theory, the video never leaves the node, all we're sending is just the occupancy information that's detected. We can do this, and a lot of this development work actually happened locally here in India. And we can tailor the algorithm for detecting cars, for detecting pedestrians. I mean, there's lots of different applications we're exploring with this technology. And this is the actual Blackfin device itself. But one of the things that's kind of really interesting about this, if we just kind of look at an example here, is that the information that gets sent up is simply the bounding box information, in this case, of the car or person. So if you were to send VGA data at this rate, uncompressed, I mean, you're looking at about 18 megabytes per second. Whereas, for a single occupant, we can reduce that down to sort of, a low number of bytes. Right, so there's extreme data compression happening here that's kind of, and it's an example of kind of like intelligence kind of at the node enabling, a very, very powerful set of compression techniques. I think the advantages here really are around, we're doing a lot more information extraction at the node, okay? It can be relatively low power and small footprint, and there's very little in the way of data transmission capabilities needed. Okay, so this will work like with very low power, low bandwidth networks, and you don't need Wi-Fi or higher bandwidth or cellular networks to be able to support this. Okay, and it's kind of a software-based sensing system, right? Which is kind of one of the areas we're exploring about. Okay, how do we put a lot more smarts rather than building large, big hardware engines? How do we put it into software so that it can be remotely upgraded over time, and even enable the addition of or the enablement of new features over software over time as the remote devices are upgraded? And of course, the disadvantage is that that the software algorithms must be managed remotely, right? And there are potentially higher security risks like any other edge device. So one other example I just want to talk about is the idea of remote vibration monitoring. Okay, so in the interest of time, I'm just going to skip through all the details here. This is an example of some systems we've put together that we have a remote sensor on this side, right, based on one of our accelerometer devices that's optimized for doing vibration sensing. And really, this is kind of used in sort of machine, predictive analytics and predictive maintenance type applications where we're doing remote vibration sensor. The thing we're doing that's on this device is we're running local algorithms to actually do some, potential error or failure mode detection before we ever send the data up to the cloud. And an example like this is an FFT, right? So typically in a vibrating system like a motor, you can see you get a harmonics will pop up in relation to sort of different potential failure modes, like a bearing that's about to go wrong, right? Or something that's potentially wrong with the load. And by monitoring for various harmonics, right, we can actually see if something is going to fail. So it's a very early leading indicator before there's any evidence anywhere else in the system. We can kind of see that, yes, something is about to fail, okay? So again, some of the advantages, disadvantages are the same. The real goal here is around data compression, right, or information compression as we send it to the cloud. And before I wrap up here, and I think I'm almost very close to time, I wanted to I was asked to talk a little bit about our Limerick Fab Monitoring Examples. So this is an example of where we're actually using some of our technologies ourselves to improve the efficiency of our own manufacturing. So, a wafer fab is a very complicated workspace, right, and work environment. The challenge we have is that we're dealing with some of our plants because our products have really, really long life cycles. Some of the equipment that's in our fabs have been around for, for decades, right? So, and are still running, and we still need to keep them running because we're having products in the field and are still selling that are decades old, right? So it's an example of what's referred to as a brownfield application. We have all of these tools and equipment, and we need to figure out a way to make the plant more effective, but don't necessarily have all the connectivity capabilities associated with it or necessary. So, so I think, you know, that one of the other areas that comes up as well is that over time, what we see is that the, you know, the new failure modes start to appear in the systems, right? So as the equipment ages in that. So we're sort of using some of our sensors like the vibration monitoring sensor, voltage monitoring, and pressure monitors and so on to accumulate more data and figure out how these systems are becoming, you know, starting to fail. And the whole goal of this is really the bottom line here, right? It's all about preventing yield busts, right? So what we don't want to do is after a sort of a 6 or 7 week lead time through a fab, you know, many expensive processing steps to find out at the end of the line, oh, the parts fail, right? And so the goal of this project that's still in process is to really sort of look at all of the online monitors or inline monitors as you go, coupled with this extra sensor data, right, to, you know, predict a yield failure prior to ever getting to the end of the line, so we can scrap a lot early with less cost and basically start a new lot as a replacement. So this is a project that is already yielding benefits for us in our fabs in Limerick, and we have a second fab in Wilmington in Massachusetts, US, where we're rolling out an exercise like this as well. So I think with this, and in the interest of time, I'm actually going to just skip through a couple of examples here of just, you know, the various different sensors that we have here, some various images and pictures and so on. You know, so this is an example of, you know, some shift in performance on one of the parameters on one of our nodes. An example of a MEMS sensor that's in here, one of our systems. The output from that, right, some of the real-time data being gathered. And then sort of finally just a picture of the overall system, because we're also pulling data from existing, you know, data sources that are built into the fab line, and then augmenting that with sensors that we add ourselves to look at voltage, vibration, temperature, and air pressure, and so on. And so with that, I'm just going to wrap up here real quickly. So the IoT multiplier effect, you know, as I said, will be responsible for a substantial amount of economic impact in the coming years. I mean, a transformative amount of economic impact. Realizing this impact will require solutions that can really close value loops to efficiently modify behavior in the real world. And automation of the data information or knowledge and wisdom processes is key to understanding how to efficiently modify this behavior and enable these value loops, okay? And the sophistication and scope of IoT systems will allow many options for implementing these DIKW processes. Really sort of, you know, depending on the application, depending on the use case, I mean, we could make these system trade-offs, right, which enable an awful lot of value to be created at the electronics and at the, you know, the edge node level. Okay, and you know, so conventional wisdom, as I mentioned, suggests that processing in IoT systems should be done in the cloud, but really moving processing to the edge node enables smarter sensors and information extraction much closer to the source. And you know, I think the key thing about all of this, as we know, is that no one organization can efficiently, you know, solve all of these problems associated with a complete value loop. So partners and supplier selections is going to be key, you know, for all of us as we kind of build this kind of brave new world together. And with that, I just want to wrap up and say thank you all for your attention here today. So. Oh, we did? Okay, great. So I've been told we have time for a couple of questions, which I'm happy to take. Oh, I'm sorry, I can't. Just, oh.
Thank you. Hi, thank you for a very informative talk. I had a couple of questions. First question is, if more and more of the intelligence is going to move towards the fog end of the IoT cloud, from your video camera example, it sounds as if we'll have to optimize based on the nature of the problem, yes, right? In other words, the software that runs at the end is going to have to be optimized. So how do you foresee this happening for multiple devices? The same video camera could be used in multiple contexts. So who's actually going to write the software that will optimize for the end thing? How do you think that ecosystem is going to work?
I think that, you know, there's a complicated answer to that. And I think the reality is that for different use cases, it may be different people in the supply chain, right? Increasingly, certainly, you know, as a sort of a semiconductor and system supplier, we're seeing requests from our customers to do it, right, ourselves, right, and supply that to them. Maybe with some, you know, we almost have this, you know, 80-20, 90-10 rule, where a lot of the work on the algorithm side, we try to do 80% of it and then allow our customers to kind of tailor the rest of it. That seems to be a kind of a good mix, right? But increasingly, I mean, the other thing that IoT enables in this space as well, right, is that, you know, the algorithms are not fixed, right? I mean, obviously they can be upgraded over time. So one of the areas to kind of explore is that, you know, is how machine learning can impact this algorithm development. So in the example of the car, right, the blip camera in the car, or pedestrian, or people monitoring systems, and I encourage you to take a look at the demo outside, is that there is an opportunity, right, for, you know, although I'll contradict myself and say that, you know, if we can send the video data to the cloud, at least in sort of early stages of deployments, then you can deploy machine learning algorithms to actually learn about how to optimize the algorithms better. So there is the opportunity to automate some of this, the algorithm development and tuning as well. So,
I have a question. So in the gateway as well as at the edge node, you talked about, and also you talked about a completely different concept where bring the analysis to the extent possible closer to the source rather than take everything to the cloud, which makes a lot of sense if you look at the volume of data that can pile up in a very short period of time. Yep. The data security aspect, I mean, the physical security, I think you covered in your presentation, but the data security per se definitely shows vulnerability, right? So is there a plan or a way forward that the system implementers need to consider early in the cycle as far as the data security is concerned?
So, you know, I think the whole question, if I understood the question correctly around, you know, the question of data security, and I think I'm looking at Doug, who's sitting right in front of you, who's going to talk a little bit about this. I think later today or tomorrow, Doug, you're giving a talk? Is it tomorrow? Yes, okay. I mean, it starts really, I think, with, so I highly encourage you go to check out Doug's talk. I mean, you know, there's the question of kind of the data integrity from a couple of different perspectives, right? So there is the accuracy of measurement, right? How well does your data represent what's going on in the real world? I mean, that can be a real, you know, a real concern. And then the second thing is if the data has been manipulated or interfered with in some way, right? I mean, the old adage for computers, right, garbage in equals garbage out, very much applies in IoT systems as well. You can't make good decisions on bad data, right? And so I think, you know, part of the, you know, the security challenge starts with, you know, paying an awful lot more attention at the node devices. That's not something I would say that, you know, that as an industry, you know, there's movements in terms of focusing on that, but I'm not sure, for example, we have a lot of standards around that today, right? And I think it starts with, you know, how do you make the devices tamper-proof so you can't get in there and start either upload or load malicious code, right? How do you protect them, you know, make sure that the identities are real, right? That you don't have an extra device on the network spoofing data that shouldn't be there. So I think these are all challenges that certainly I think us and a lot of other suppliers are struggling with at the moment. But I think that, you know, I think the fact that there's an awful lot of focus on this area right now, that you will start to see, you know, progression and sort of, you know, a lot more movement on this space. Because I think the challenge with IoT, when we talk about the economic impact, it's only going to be realized if we can scale. Right, we hear about 20 billion, 50 billion, 100 billion connected devices, right? If, you know, we can't solve some of the security, some of the provisioning, some of the logistics, you know, around getting those devices into the field and trusting them, right, then the vision will not be realized.
One supplementary question, in the signal path diagram that you showed, you had inserted a digital signal processing block for the kind of you know, applications, examples that you showed. Don't you think that will be a power guzzler kind of thing, or we have very power efficient systems because the signal processing will bring in a huge demand on power consumption? Yeah.
So I mean, I think what we notice is that, you know, certainly, you know, with the advent of kind of, you know, modern processes and, you know, the ability sort of, you know, certainly if you look at how microprocessors and microcontrollers have benefited, right? You know, you can do an awful lot for a given power footprint now. You can do an awful lot of local processing, right, right on the edge node today compared to previously. And I think that, when you look at the trade-off of that versus sending data, transmitting data to another link, I think that, it sort of opens up an opportunity to, or almost like forces you, if you really care about power, to try and optimize the amount of data transmission that you're doing over time.
Okay,
So
thank you.
I have to say I'm having a little trouble hearing the question, so I hope these I did answer your questions. Okay. And I know there was a question just right in front here. I'm sorry, I hadn't.
Is audio and video transmission also possible across sensors?
I think it is. Okay, but I think that the question is that in this specific use case, right? I mean, how required that is, because audio and video bandwidth is very expensive. Now, admittedly, you can do it over Wi-Fi, and there's lots of, anyone who has a smartphone knows you can do it over a very long distance. The question is that when you get into these sort of small footprint devices, is that the most efficient way to, to solve the problem, or can you do some processing on the audio video locally to be able to, compress the data and then send the results upstream. So the two examples I gave here, I mean, vibration is often, not always, but represented in, you can hear it, right? And whether it's, in the audio spectrum or the human, hearing range or beyond, but it's, in some respects, vibration is an audio signal, right? And MEMS, to some extent, we use them as audio transducers, right? Although very specialized ones. So I think that, these two examples are areas where we chose not to transmit the data and basically try and send the results instead. So it's definitely an option, but I guess it's part of the whole system trade-off. Is it the most optimal way to do it? I mean, there's certainly people doing that, doing video processing on the cloud, right? So, but as long as you can tolerate the power and the sophistication needed to get the data to the cloud in the first place, then yes, of course, it's a very viable way to do that.